ready? Are you mad inside? Got you strapped down to your seats. Out of the doorway, bullets rip full clip. Gone speed approach, follow my lead. Fire winds gust, empire crush, full thrust. Full in the whole row with the rush. Untouchable chunk of an earwax assault. Sound wave slave out the back cave smoke. My belly full prance dance avalanche quote. Down slope, elegant ass fantasia. Killer whale tail in the hell, black male from Asia. All out the woodworks, hood shirts and wizards. No match, unhatched. The rap is rigid in the shaft. Shiny cop, hip hop to the limit. Night watch, path mark, spark, spin a quake, nuclear blast. Heavy on the cash, give it what it takes now.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
The diabolic witty dialect stalker in Gotham City, with the possibility to stop your walking ability. God forgive me, spark enemies with pistol grips. The missile tips impact hit you so hard, official script strike with physical hits. You visible watch for the imperial blitz. Serious mid, subject to the wreck war tones. And door poems liver than WWF war zone. More component Gotti tracks, bodies collapse. Rap for lottery stacks, shatter like when pottery cracks. Logical facts from the terror dome. Spill from the guts, drill till you bust. From where you bust and guard you now we trust. Told you like hounded mutts. Pound pumpkin sound struck clown what? You'll get drowned in the cut by crowd roundup.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
Hey yo, I spit bars, traveling tremendous speed, measuring far. Which watching satellites circling Mars. Verbal onslaught, bring forth physical force. Up 100 wild, pal in the Trojan horse. Thought method, set it on generic mic ethics. Professional next, left foes beheaded. This music is mind control like computer chips. Been doing this for numerous years, refuse to lose it. With jungle tactics, maneuver like a trained soldier. Hall of Fame, flamethrower, take aim, it's game over. Ayatollah, high roller, nine-toter, mind controller, 2009 time quota. My coalition, bring the demolition. Wu blade incision, slate the competition with no intermission. Spitting hazardous darts up front like Rosa Parks, make a million men march.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
Who got next? Meth got next, I chin check all these MCs, line them up guard, I go jihad. Declare holy war, it be hard to dip and dodge. Police squads trying to bogard, we rip and raw. The boulevard ain't safe for your kids, that's how it is. In the ghetto we ain't scared to death, but scared to live. So Goldie, mosey to the spot, get that moldy. Rusty ass 38 special, owe me. Slowly I turn, face the one and only. Naughty by nature, do my dirt all by my lonely. Ass pretty Tony, when I got up, keeps up. 36 chambers, enter at your own risk. Take that watch off and tuck your necklace. City never sleeps, streets is restless. Rap style will slay you when you least expect it. Pull a plug on your respirator, leave you breathless. Wu-Tang forever and a day better. On your boys, I deploy battleship raps, seek and destroy.
Rage, rock, roll, fight, roar, fall, rumble. Rage, rock, roll, fight, roar, fall, rumble.
All right, so this marks basically the halfway point of the course where we transition into more data structures and algorithms. So it gets a little bit more theoretical, but it's going to be told from a more practical point of view. At least that's how I do it. So we are online, so if you have any questions, go ahead and post to the YouTube live stream here. But otherwise, the first data structure that we're going to look at is something that you're already familiar with because you've been using it in Java. You've been using lists and array lists. And now we're going to get some more we're going to understand how those actually work. And the motivation should be clear here that dynamic data structures like lists, sets, and maps, which are supported in pretty much any programming language other than C, are way better than simple arrays, right? So why? Well, because if I create an integer array here, int n is equal to 10, if I go ahead and create an integer array of size 10, right? Array, new integer dot of 10, there we go. If I create an integer array of size 10, that's it. It can never be of size 20. It can never be of size 5. So if I don't only put 5 things into it, then I'm wasting space. If I try to put 11 things into it, then I'm going to run out of room and I'm going to have an index out of bounds. If I put something at the very beginning and at the very end, then I've got this huge gap in between, right? I don't want to have to worry about those low-level details. This is even worse in C, where you're not only doing this manually every single time you want to create an array, but you're also passing around the size of the array to every function. You're going to have to make sure that you clean up after yourself and free up the memory after you've allocated it and you're done using it, et cetera, et cetera. What I want to do is I want to write a data structure now that takes care of all of those details for me. I'm going to go ahead and create my integer array list, and we're going to iteratively improve this as we go along. Right? We want to leverage the object-oriented programming principles that we've covered up till now. We want to make sure that we've got good encapsulation, that all of the details are encapsulated inside of the class so that we don't have to worry about what happens when we insert something. Is it big enough? Is it going to be able to hold it? Or we want to make sure that we have abstraction. We don't want to have to worry about how that thing actually gets done. We just want to put stuff in, take stuff out, do whatever we're going to do with it. And of course, we eventually want a good polymorphism, probably by Friday, because I don't want to have an integer array list, a double array list, a string array list. Instead, I want one array list that will be able to hold anything, right? So let's go ahead and get started, right? Again, arrays are bad. Once created, the size is essentially fixed. We have to do a lot of bookkeeping to keep track of which indices have been used, which ones are free. Deleting or removing elements may leave gaps that we have to take care of. And of course, the solution is to use a dynamic data structure called a list. So solution is a list data structure. Structure, there we go. We're going to want a couple of things out of this, right? We're going to want to be able to automatically, we want it to automatically grow and shrink without having to worry about the details. I'll say, right? We want the ability to add stuff, right? We want the ability to retrieve stuff, right? We want the ability to remove stuff. Retrieve, I before E, except after C. Yep, good. Remove stuff, and then maybe modify stuff, right? Do those 4 things look familiar to anybody? What if I called them create stuff, retrieve stuff, update stuff, and delete stuff? CRUD, right? The same 4 basic operations that you can do on a table, you can do on a data structure. Why? Because a table holds stuff, a data structure holds stuff, right? So we're going to want to support all of these things, right? We want to make sure that all the details are encapsulated inside of the data structure so that we don't have to worry about those details. Oops, there we go. And we want good abstraction. We want to use an interface that specifies how to use the list, not necessarily how it works. In other words, if I'm going to use this list, I want to be able to put stuff in and it takes care of all the details. I want to be able to pull stuff out and it takes care of all the details, right? Let's come over here and get started. I can't get away from arrays. That's how things are stored at the bottom level, right? So I'm still going to have a private integer array, right? ARR, there we go. But it's going to be private, so I'm going to close off the outside world to seeing this array, okay? Now let's go ahead and create a default no argument constructor here, a way to create a list. So public my integer array list. What should this do? Well, before we do that, let's come over here and as an alternative to that array there, let's go ahead and create that list. I'll call it numbers is equal to my integer array list. Right. Now, I haven't written anything else. Before I write anything else, let me ask you, what would you expect to be in this list as of line 11 right now? What's in that list? Have I put anything into that list called numbers yet? No. So what's its size? It's probably 0 at this point, right? If you want to depict this as the internal array here, it's of size, some size, right? And the size is 0 because you haven't put anything into it yet. Okay? Well, I can go ahead and create an array. This dot array is equal to new integer of 0. Right? Is that very useful, an array of size 0? No, you've just wasted a bunch of memory, a small amount of memory, but you've wasted a little bit of memory because it can't hold anything. What if I change this so that it could hold 10 elements? In other words, I made it look something like this. 1, 2, 3, 4, 5, 6, 7, 8. There. Too big. Right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? Would you say that the size is now 10? Have I put anything in there yet? No, I wouldn't say that the size is 10. What would you say 10 is? Think of this like a box that can hold 10 books, but there's no books in it. Would you say that there are 10 books in it? No, you'd say that the size is 0, but it can hold 10 books. What kind of a term could we use for that? Capacity is 10. There we go. Okay. So the capacity is 10, but the size is 0. Probably want to keep track of that. This dot size, initialize that to 0, meaning that you need to put that into a variable. There. We've got the beginnings of a dynamic list here. Okay? Come back over here. We want a way to add stuff. Got to start somewhere. Right? Can't remove stuff or retrieve stuff if you can't add stuff. So let's go ahead and do that first. Public void, say, add element. We're going to take an integer x and we're going to add it to this list. Let's document that. Adds the given integer x, or element, code x, to this list. Dot, dot, dot. How? So here's our list over here. Let's go ahead and say that I want to add 42 to it. Where would you put it? With no other qualifications. Would you put it over here? Probably not. Would you put it right there? Would you put it, where are you going to put it? At the first available spot. If you think about this more generally, and you've eventually got a list that has, say, 10, 20, and 30, and you just want to add 42, what's the most natural place to put it? Are you just going to randomly put it somewhere in between? Probably not. You could put it to the front of the list, but what's most natural, maybe? To put it to the end. All right, let's do that. Adds the given element to the end of this list. There. I put that into the documentation. If you want to, you can, of course, come back here and say add element to end. Right? Or you could go ahead and rename this entirely. The most appropriate name here that I would think of if I were doing this in real life would be append. Right? You're putting it to the end of the list. There are plenty of others. For example, push. Right? From Python, how do you add something to the end of the list? You push it. Right? I'm going to go ahead and stick with add element. I don't want to get fancy. Because in real life, you would actually not write this class, right? You would use the array list because it's already done and written for you. So let's go ahead and add a couple of things to this list. Numbers dot add element. Let's go ahead and add 42 here. Let's go ahead and add 101. And let's go ahead and just go into a big loop here. For int I equals 10, I is less than or equal to 100, I plus equals 10. What I'm going to do is I'm going to add 10, 20, 30, 40, 50 into it. Numbers dot add element I. There we go. All right. I've set up my tests. I'm going to expect it to be 10, 20, 30, 40, all the way up to 100, then 42, and then 10 at the end. Let's go ahead and just get rid of that. All right. I'm going to expect that there are going to be 11 things in there. We actually, of course, need to implement this first. Where are you going to put that element? So if you're starting out with an empty list, where do you put it? Right here at index 0. If you're starting out, or if you have a list currently that is 3 elements with at indices 0, 1, and 2, where are you going to put 42 now if it's at the end of the list? Index 3. What was the size before? 3. What was the size of this? 0, right? And so you're going to put it at index 0. You see a pattern? This dot array of this dot size is equal to x. There, I put it in. Right. Does it work? Seems like it. Right. No news is good news. Right. Well, I'm not actually printing anything. How could I tell if this worked or not? I could fire up a debugger, walk through it. What's a quicker way of doing it? Just ad hoc. What if I were to print it out? System.out.println numbers. Default behavior of the toString method. So let's come over here and write a toString method so that we can actually print it out. Public string toString. Okay. There we go. I'm going to go ahead and create a string builder. SB is equal to new string builder. And I'm going to append onto it each element in the array. But before I do that, let's make it look pretty. I will go ahead and append an opening square bracket with a space. And at the end of it, I will go ahead and append a closing square bracket after a space. And then everything in between for int I equals 0, I is less than this dot array dot length. Is that right? I'll go ahead and sb dot append this dot array of I, and then sb dot append a comma and then a space. And then finally at the end, return sb dot toString. Oh, okay. Thank you for the shout out, whatever that means. There we go. 42, no. Does that look right? Nope. Back to the drawing board. First of all, what about these nulls? I'm printing my capacity. Remember, this is the capacity, not the size of the list. If you only want to print out the things that are in the list, what should you be doing? This dot size. That takes care of a little bit of the problem, but not all of it. It changes the problem. Right? All right, if you add an element, right, so it's a 0, there's nothing in that list. When you add 10, how big is that list now? 1. If you add 20, 30, 40, how big is the list now? 4. Right? 10, 20, 30, 40. If you add another thing, 50, how big is it now? 5. Are we taking care of that bookkeeping? Nope. So what should I do after I add an element? This dot size plus plus. I like that. Let's go ahead and try and see if it works now. Actually, I'll go ahead and say, suppose I'm not doing this just yet. 10, 20, 30, 40, 50, all the way up to 100. It works, right? In fact, I can print this out on each iteration and show you that each iteration works. Right? 10, 20, 30, 40, 50, all the way up to 100. But the moment that I try to put in that 11th element, what happens? Index out of bounds exception. Wait, array index out of bounds. What the hell is an array? I've got a list. Right? I've got a list. Should I have to worry about anything to deal with arrays as a user of this list? Probably not. That's called a leaky abstraction. You are leaking information about the internal workings of how this list is implemented, right? If I had just called this list instead, right, would you expect to have to deal with anything with respect to an array? No. So let's go ahead and fix that. Once it's full, we're done, right? Once I put 10 elements into an array of size 10, remember our capacity is only 10 here, what do I need to do? First, check if the array is at capacity, in other words, full, then 1, create a new array that is larger. You don't want to lose any of that information, so copy over all the old elements, right? And 3, make this list's array point to the new larger array. There's my outline. Once it's bigger, then we can put stuff into it. Okay? If there's only 10 before, let's go ahead and make it to be 20 now. Right? So first of all, check to see if the array is at full capacity. What kind of condition is that going to be? If the array is of capacity 10 and your size is 10, then you know that it's full. So what do I check? This dot array dot length is equal to this dot size. That means it's full. We need to create a new array that is larger. Integer bur is equal to new integer of just slightly larger than the old one. So this dot array dot length, let's just go ahead and make it plus 10. So if it was 100 before, now it's 110. If it was 10 before, now it's 20. Right? Okay. Let's copy all over all the old elements. For int I equals 0, I is less than this dot array dot length, I plus plus. There's got to be a better way, right? BRR sub I is equal to ARR sub I. Great. Make this list new point to that old one. Everybody in here has done this in C. This is called a deep copy function, right? So this array is point to the new one. This dot ARR is equal to BRR. There we go. That line itself is a shallow copy. If you're if you remember back to your C though, what have we lost? We have a memory leak here technically, right? If this were C, because we never cleaned up the old array. There's the old array that was of size 10, the new array that's of size 20. We copied everything over and made this reference now point to this thing over here. We should have cleaned that up first. We should have freed it up first. Do we have to worry about that in Java? Nope. Why? Automatic garbage collection. There is no way to clean it up, actually. Right? There's no way to free it up. There is a little bit better way of doing this, though. If you can replace 3 lines of code with something that's built into the language, you do it. This dot array is equal to arrays dot copy of. Hey, who would have thought that it was so common to have deep copy functions that they made one for you. And in fact, they made several for you. This dot array, and then the new size is going to be this dot array dot length plus 10. Anybody coming from 155H, you would have done this, right? With the copy functions that we would have assigned to you, we were just expecting you to reuse arrays like dot copy of. What's this second argument here? That's the size of the new array. So if this were simply just the old size, then it's taking these 10 elements and copying over these 10 elements. If it were less, right, then it's taking these elements, but it's only taking the first size of them and copying them over and making a smaller array for you. If it's plus 10, it will copy over these 10 elements and then also pad it out with a bunch of zeros at the end so that you now have a larger capacity. All right, let's see if that solved their problem. It did. Great. Check mark. Add stuff. Before we go on, though, do you always just want to add something to the end? I like my data structures to be a little bit more flexible. Maybe I want to add something to the beginning. Maybe I want to add something to the middle. All right, here, let's go over here. 10, 20, 30, 40, and 50. And I want to add 42 here. Maybe I want to add something to the beginning. In other words, at index 0. If I do that, should I get rid of 10? That doesn't sound like adding something. That sounds like modifying or removing something. So if I did that, let's say 0, 1, 2, 3, 4, and 5 as a placeholder here, What would you want to do if you wanted to add it to an index 0? Move stuff over to make room for it. Now you can add 42 right here. Right? Okay. What if you wanted to add 42 to, oops, that's not what I wanted. What if you wanted to add 42 to, say, index 2? What would it look like then? You'd take everything here and you'd shift it down, making room for your 42 right here. What if you wanted to add it to the end? Let's get rid of this. Do you need to shift anything down? Nope. You can just put it there. That sounds familiar. Did we just not do that? Right. So probably, not only am I going to want to write this function that allows you to insert it anywhere that you want, but also I'm probably going to want to do some error checking, and also maybe refactor that other one to not have to have two functions with repeated code everywhere. Okay? Let's do that. Public void add element at index. So we'll add the element x at index, int index. Okay. Let's document it before we go on, because documentation often tells you what you should be writing, right? Adds the given element x at the given index. Automatically shifting stuff down. There we go. There we go. Oh, how embarrassing. Not really. You're all adults. All right, so add element at index. Where do I put it? Besides, it wasn't even spelled right. It's two T's, right? Okay. I'm not sure that the spell. I'm not interested to check to see if the spell checker would catch that or not. Who cares? Add element at index. So the first thing we want to do is what? Shift stuff down to make room for x. Dot dot dot. So what is that going to look like? Suppose that I wanted to do it right there. Right. I wanted to add it at index being 2. Right. Should I just go ahead and start right here and take 30 and move it over here? What happened to 40? I lost it. Right. So should I work from the left to the right? What if I work from the right to the left? That's way easier. Take 50 and move it over here. That leaves room for 40. Take 40 and move it over here. That leaves room for 30. Take 30 and move it over there. And now you're done, and you can add in 42 here. So let's rethink this. Start at the end. Right? Dot, dot, dot. Copy array sub I into array sub I plus 1. Okay? Until what? Where do we go until? We hit I is equal to index. Good. Right. So for int I, where do we start again? At the end. Where's the end? Size, careful. Size is 5. 0, 1, 2, 3, 4. So it should be size minus 1. I is copy over. ARR sub I plus 1 is equal to ARR sub I. There. Now I've made room for it. I can go ahead and add it. This dot array of index is equal to x. I should be doing this dot, this dot, this dot. There we go. Okay. What else should I do at the end? If there are 5 things before, and you added 1 right in the middle, how many things are there now? 6, so this dot size plus plus. Uh-oh. What happened? What did I do in this other one that I'm not doing here? Checking for the capacity. So let's go ahead and copy paste this over here. First, make sure that the capacity is there. Should I be copy and pasting? Copy and pasting. Probably not. We'll take care of that here in a second. There we go. 10, 20, 30, 40, all the way to 100. Where did I put 42? At index, what was it? 3. 0, 1, 2, 3. Looks like it works to me. Let's go ahead and keep trying some things. Corner cases, 0. That's adding it to the beginning, right? 42. Add it to index 8. What should I expect then? All the way up to 80 and then 42. What other index should I try here? Maybe 9. That'll be 90, 42, 100. Then 10. Where would that be? At the very end. Hey, that looks familiar. Add element to the end. Should this function call that function, or should that function call this function? Which one's more general? Certainly this one, because you can achieve this one. You can achieve add element by simply using add element at index. So let's get rid of all of this. This dot add element at index x. What's the index that we want to add it at, though? There are 5 things in there. 0, 1, 2, 3, 4. Where do you want to add it? Right here. This dot size. Good. Let's come over here and see if it still works. Yep, regression testing. You've changed something, not the interface, but you've changed the internal workings here to make it a little bit more efficient or to reduce redundancy in your code or whatever. You need to make sure that it works. Should I be doing this all manually like this? Probably not. Right? This is all ad hoc. Every change that I make means that I would have to come back and repeat every test that I was doing by hand. You don't want to do that. What kind of thing would you use to make sure that you could test all this stuff rigorously? What's that thing in Java called? That you do every week. You turn it in, and I just run a big giant script to execute it. No? JUnit, unit testing, right? Except not the last 2 weeks. Last 2 weeks with the SQL, I don't know, maybe it's not worth it to look into seeing about unit testing for SQL for me, but each those 2 weeks are just hell for me because I have to go through and manually grade all 150, 200 submissions of SQL stuff. Thank you to those that turn in a perfect script because it's just look at it and I'm done with it. It's the ones that are, buggy or that I have to look at it really closely and say, does that deserve partial credit or not, right? All right. So thank you. Anyway, come back over here. Looks like it still works. Should I be able to add something to index 11? Let's find out. Oh, it seems like it works, except that instead of 42, I've got null here. What's another potential bad index that I could add at? -1? What's going to happen there? An array index out of bounds exception? Again, should I be worrying about arrays? I've got a list. Why are you telling me about arrays here? You've leaked information about your internal workings to me. Don't do that. You take care of that. So before we even do anything, we do some basic error handling here. If the index is negative, or if the index is greater than something, then we say, nope, you can't do that. Throw a new illegal argument exception. Right? And we'll just say invalid index. Right? Of course, normally you would throw a list index out of bounds exception of some sort, right? And index. There we go. What is that thing right there? Remember, if it's size 5, 0 is fine. 1, 2, 3, 4, that's fine. What else is fine, though? 5 is also fine. So strictly greater than this dot size. Right? Because if it's this dot size, then that's fine. That means you're just adding it to the end. Right? Let's run this and see if it works. Oh, well, of course it's not going to work. But now it's an illegal argument exception. You're not telling me about your internal representations. You've got good encapsulation, right? Remember, encapsulation is information hiding. You are hiding from the outside world how this actually gets implemented. so that they don't have to worry about it. So let's come over here and change this back to something that we do know that is okay. 3. 10, 20, 30, 42. All good again. Pretty good. Add stuff. You could add a bunch of bells and whistles on this. Add element at start, right? Add random location, right? You could do all that stuff if you really wanted to. But because we already had that one method that's the most general, add it to any arbitrary index, all those are just one-liners. What about retrieving stuff? Oh, well, you've got a toString method. That's retrieving stuff, right? No. What if you want a specific element? Public int get element. Which one? At the element at index. I like that. Return this dot array of index. There we go. Good enough? So let's try to get a particular element, right? So int x is equal to numbers dot get element at index 3. What should I expect back? The thing that I just put in at index 3, which is what? 42? Oh, looks like it works to me. Get element at -1. Same thing as before. Ugh. Oh, what happened there? Oh, there. Let's change the wrong thing, that's why. It should be an index out of bounds exception. Again, we're leaking information about the internal workings here. So let's capture that value. And if the index is negative, or if the index is greater than or equal to, in this case, 0, 1, 2, 3, 4, 5. If the size is 5, you should not be asking for this guy that doesn't exist. You can add something there, that's perfectly fine. But if you're asking for something that doesn't exist, we're going to throw that back at you. Right? Invalid index. There we go. Invalid index -1. Invalid index 15. There we go. All right. Undo, undo, undo. There. Back to good. That's it. You're not pulling stuff, I mean, you're not removing things, so we don't have to worry about the size. You're just retrieving it and returning it. So, add stuff, retrieve stuff. How should I know not to ask for that thing, though? 30. Give me the thing at 30, right? If I want to be defensive about it in this class right here, what more information do I need? If the size of the list is at least 31, then grab the 31st element. Right. Dot, dot, dot. Do I have enough information with this implementation to be able to do that defensively? No, not yet. So let's add it. Public int get size. Oops, there we go. Return this dot size. Now I have enough information from the outside world to write defensive code if I want to. Okay? No, that's not something you should be asking for. All right. Remove stuff. Modify stuff. Let's do modify stuff first. Public void for now. Replace element. Int x int index. So let's document this. Replaces the element at index at the given index with the element x. There we go. Is it common still? Is it common in high schools to learn HTML? Yes? No? Like, is there an HTML course, or they just focus on Python, Java? Oh wow, 2. So CSS, JavaScript. Okay. Did you? Okay. All right. At least you got JavaScript. Cool. Right. You learned how much you hate JavaScript. Oh, you love Java. Okay. All right. Anyway, let's go ahead and replace that element. This dot array of index is simply just going to be x. What else should I be doing? First of all, do I need to check the capacity? If that thing already exists and you're just taking it out and replacing it with it, then you need to increase the capacity, decrease the capacity? No. But what should I be checking? That you're wanting to replace something that exists. So, if you're asking for something that doesn't exist, we'll go ahead and throw this back at you. Hey, you know what? Copied, pasted, copy, pasted, copy, pasted. You might want to put that into another method. Right? In fact, let's just take these two and put it into one method. Oops. Public Boolean is valid. All right, indices valid. Are valid is valid. Valid index. Indices. There we go. Int I, int j, or int index. There we go. And I will simply just cut and paste that. And instead of throwing a new, well, I could do it this way. Public void, right? And here, let me call it something different then. Because it's now no longer a Boolean function, we'll go ahead and check indices. Check index, because there's only one. There we go. There. Now I've got the proper name. And if that's the case, then I can go ahead and just call that check index. Right? And I can call this dot. What are you complaining about? Oh, index. There we go. Code reduction. Code reduction. Right? Now, if somebody asks for something that doesn't exist, we have one common place to do that. If you want to, you can go ahead and do the same thing for this, but remember, it's a little bit different. It's greater than or equal to. Right? Down here, yeah, up here, it's strictly greater than. All right. That's good. But before I go on, let's really think about that. Where was it? Here it is. I made it public. Over here in demo, let me try. Let me ask. Numbers.check index. Right. Is 10 a valid index so that I can add to it? Numbers.add element to index 10. Right. Is that add element to index or at index or whatever it is? Is it at index? These are terrible names, but that's why. All right, so should I be forced to check something? Should I be even be able to check something like this? Before, when they were in those other functions, right, nobody had access to them. Why should we be giving you access to something like this that's internal, right? Private. Again, making this public is a leaky abstraction. I have leaked information to the outside world through my interface that there's something going on underneath the hood that I'm checking these indices to make sure that they're valid every single time. I'm going to make this private so that I'm not exposing that to the outside world. If you have a reason to do so, then maybe, okay, I go ahead and do it. Like, for example, get a size. That's a public method. But checking an index to make sure that something's not going wrong, that's probably private, right? That's private. That's not going to be part of the public interface. All right. Replace element. All good. So let's go ahead and replace 42 numbers dot replace element at index with, I don't know, 43. There we go. Let's print it out to make sure that it works. Oh, nope, sorry. Print numbers, not X. There we go. All right, so 42 has now been replaced with 43. Looks good to me. Okay. So we have two ways of adding stuff. We have a way of retrieving things by index. We have a way of modifying stuff. Let's have a way of removing stuff. What's that going to look like? If it's like this, we'll go ahead and say that it's like this. There. There are 6 things in there now. What if we wanted to remove 42? Should I just go ahead and remove it? What happened there? We've got a gap. just the opposite. All I'm going to do is shift stuff down now. And here it is perfectly fine to go ahead and go from left to right. Right? So let's remove that element. Public void remove element at index. Hey, what should I do first? Check that index. Right? Now that I've got a function to do it, it's really easy. Right? Otherwise, shift stuff down starting at index. So for int I equals index, I is less than this dot size, I plus plus. This dot array of I is equal to this dot array of I plus 1. All I'm doing is taking I plus 1 and moving it into I plus 1 moving it into I plus 1 and moving it into I. What else should I do? Don't forget, there are 5 things in there before, and you've removed one of them. How many things are in there now? 4. So this dot size minus minus. Let's test it. Replace that element. Remove that element at index 3. Hey, looks like it works to me. Good. What else might you want to think about with respect to remove element? When we filled it up, 10 to 10, right, we increased the capacity automatically. What might you want to do now if you're removing stuff? Consider what? Shrink. What's the opposite of grow? Shrink. Shrinking the array. I'll put that as a to-do. Okay. One last design consideration here is, what if you wanted to remove the element, but I want to take that out, but I want you to give it to me, right? So in basically 2 operations here. Remove the element from the list and shift things down, fine, but also I want it back. Int y is equal to this thing. Make sure that it's still out of there, but let's find y there. So my design right now is a void function. It's not returning anything. Let's go ahead and change it to an integer here. Return this dot array at index. Can I do it right there? I've already shifted everything down. It's gone. So what should I have done at the beginning? Return it right there? Compiler is even smart enough to figure out that that was dumb code, right? Int temp is equal to this, then return temp. Save it off, then overwrite it, decrease the size, and return temp. Yay, 43. That has me rethinking some of my other methods now, though, right? Replace element. If you're replacing x with, or you're replacing something with x, let's go ahead and save that off. This dot array of index, we'll save that off into temp, and then return temp, so that you're now returning an integer. That makes it a little bit more flexible, right? Here, go ahead and replace that thing over there with this thing. Okay, I'll do that for you. And also, here it is. Do you want it or not? If you don't want it, where does it then don't capture it. If you do want it, then do capture it. I'm making it more as flexible as possible. I'm returning something back to you. It's it's on you if you ignore it. Right? It's your decision. Right? Everything's still good. But it's a little bit more flexible now. Last thing today, let's go ahead and, here, copy this. Right? This is great for what? For integers. Now I want to double a list, or one for, say, strings. My string array list. There we go. And let's make it so that it only holds strings now. What are the changes going to be? Now it's a string array. There we go, there we go. Add element, did that change? No. Add element at index, that changes, but only, oops, only this part right here. Now x is not an integer anymore, it's a string. What else is up here? So is that one. There you go. What about this? We're going to return a string instead of an integer. We're going to return a string instead of an integer. What else? This becomes an integer. We return a string. And our temporary value needs to be a string. Keep going. What else? String, string, string. There. All I did was change a bunch of ints to strings. Should I be doing this in two different classes? Compare with each other. All I did was change any instance of int into string. Did I actually change any of the actual code? Nope. So what's the real solution here that we won't get to, but we'll get to on Friday? Don't call it string list. Call it my array list for elements of type T. Right? This is where that last part comes in, polymorphism. You only have to write this once for any type that you want. Right? And then never write it again because you're going to use the array list that's built into Java. Right? But we're learning how the array list actually works. Undo, 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 and we'll finish it up there on Friday. 1 week from today is two things. First of all, if you're speaking of the wind here, but if you want to come running with us, it's the first of the month, first Wednesday of the month. It's April 5th. Meet outside the shore center if you want to go on a 5K. After you're done with your 5K, you can fill up on pizza at the student advisory panel. From 11 to 1, so during this class, unfortunately, from 11 to 1, you can go over to the Avery 348 and share your thoughts with faculty, with other students. Obviously, I won't be there until the very end because I want some pizza. And so we might end like 5-10 minutes early or something and head on over there and have some pizza. Right? So I would invite you to come on over with me.